Alright, here we've got a ethylene heating problem. Ethylene is heated at a constant pressure from 5 megapascals and 20 degrees Celsius to 200 degrees Celsius. Determine the change in ethylene's specific volume as a result of this heating. Alright. Well, at this pressure and temperature, ethylene exists as a gas. Sorry about that. I got some gnarly nails here. By gnarly, I mean gnarled. Anyways, so determine the change in ethylene's specific volume as a result of this heating. At this pressure and temperature, ethylene is a gas. Okay, so yeah. Let's double check that. Hold it. Don't know why I'm second guessing myself. I've already done this problem. I hope I did it right. Here's to hoping I don't lead you guys astray. Alright, so this is a gas, and we're going to be looking at the ideal gas law. PV equals RT, where R is specific to ethylene, and V is the specific volume, because that's what we're looking for. We want an equation that uses the specific volume because we want to find it. Alright, we're not actually interested in the direct specific volume. We're determined in the change of this in this specific volume. So it's got constant pressure, so P is just P. We want the change in the specific volume. R is, of course, a constant. And T has a change. Let's go ahead and solve for the change in specific volume. Alright. We can go ahead and solve this. Yeah, I don't see any particular problem. Normally with the temperature being multiplied by R is usually given in terms of Kelvin. And in the particular table I'm using here, table A1, the gas constant is given in terms of Kelvin. The good news is that Kelvin and Celsius have a constant difference, so we can write this delta T as being the temperature in Kelvin 2 minus the temperature in Kelvin 1. Alright, and the temperature in Kelvin is equal to the temperature in Celsius plus 273 degrees. Okay, so when we do that, naturally the 273 degrees cancel out, in case you needed to actually see this to believe me. So then the difference in Kelvin is just the same as the difference in Celsius. Okay, so we don't actually have to do any conversion here. Let's get rid of it. Dang it. Okay, so get rid of that. Alright. That is not what I want to do, and you know it. Dang it, stop that. This is why I hate using paint. Okay. So, our delta T is the same in Celsius as Kelvin. So, we could just look at this and say, well, that's 180 degrees. Alright, so delta V equals our R, which is in terms of kilojoules per kilogram times Kelvin. Let's see. Okay. The unit here that's used here, it says, is equal to the same number in kilopascals times meter cubed per kilogram times Kelvin. We're going to use this equivalency because we have our pressure in terms of pascals. We really don't have any energy expressions. Nothing that's usable like this anyways. Okay, so we're going to look at the ethylene. Let's move it up there. Oh, there we go. It's right down at the bottom, lines up neatly. Alright, so that's 0.2964. Okay, so this is 0.2964. Want to make sure we get our units in so that we're looking at the right thing. Can verify that our answers are correct later. So let's go to the bottom. This is kilopascals times meters cubed divided by kilograms times Kelvin. Kelvin's on the bottom, right? Yeah. Okay. Kilopascals times meter cubed over kilograms times Kelvin. Okay. Times our delta T is 180 degrees. We can call this Celsius or Kelvin because it's a delta. It does not matter. So we're going to call it a Kelvin because that's what our R is in units of. 5 megapascals, that's 5 times 10 to the 9th pascals. This is going to be divided by 10 to the 3rd pascals. This is per kilopascal. So that equals 5 times 10 to the 9th, 10 to the 6th kilopascals. Okay, that keeps it in units that we can cancel out. 5 times 10 to the 6th kilopascals. Kilopascals cancel out. Kelvin cancels out. So we're left with, let me do some calculations really quick. Okay, so this comes out to be 10.6704 times 10 to the negative 6